Hello, am I audible?
Yes, sir, you are audible.
Okay, and is my white skin is visible?
Yes, sir, white skin also visible.
Okay, thank you.
Sir, last session I missed. Do we have anything to get the access of this if it we are recording?
I think I have sent the recording to the NPTL, so they should share by the now.
Okay, sir. Okay.
Okay, so I will start discussing about the simple harmonic motion. So hello everyone, this is the second live problem solving session of the course Physics through Computational Thinking. So first I will go through some basics things about the simple harmonic motion. So simple, first of all, the uh, periodic motion is a motion that uh, repeats itself at a regular time interval. So periodic motion is a motion that repeats itself uh, at regular time interval. So basically, like you have something, you are rotating the, I mean, if there is a wheel, then this point it is rotating. So after a certain time, this point will go through and then come here. So this is a periodic motion. This is an example of periodic motion. Now period. So period is that the time taken to complete one oscillation rotation. So period T, capital T, period is usually denoted by the capital T. So that is the time taken to complete one oscillation or rotation. So basically now this point of the wheel comes after the this point of the wheel rotates and come to here at this point after for example 5 seconds. Okay, so now so we can say the period of the time period of this motion is capital T equal to 5 seconds. Now the third thing is frequency. This is f equal to 1 by t. So basically, like this is this frequency denotes that how many occurrence is happening in unit time. That's why it is 1 by t. So for here, this is the frequency is 1 by 5, which is 0.2. But if the t is something like 0.1 second, then the frequency will be 1 by 0.1 10. So if there is a periodic motion that has a time period of 0.1 second, that is after 0.1 second the motion is repeating itself, so then the frequency will be 10, or you can say 10 hertz. So now there is a very basic example of example or problem for this. Consider a imaging device that produce ultrasound by oscillating with a period of 0.400 microsecond. What is the frequency of this oscillation? So as here it is mentioned that it is oscillating, so we can assume that this is a periodic motion. So the t is 0.400 microsecond, which is 0.4 into 10 to the power minus 6 second. Now frequency equal to 1 by t, which is 1 by 0.4 into 10 to the minus 6 equal to 2.5 to 10 to the power 6 hertz. So why this is called ultrasound? So here you can see the uh, human hearing range is uh, 20 hertz to 20,000 hertz. So this particular frequency lies above this particular range. That's why it is called ultrasound. Now after this basic example, what is simple harmonic motion? So this motion is a specific periodic motion where the acceleration acceleration system or the net force of the system is proportional to displacement and acts in the opposite direction of the displacement. So simple harmonic motion is a specific periodic motion where the acceleration of the system, this motion is periodic, but also the acceleration of the system or the net force of the system is proportional to the displacement and acts in the opposite direction of the displacement. So basically F is the net force which is proportional to negative x, or A is the acceleration which is proportional to the negative x. So now I can show you an example. So this is a mass m attached to the wall with the spring, with the help of spring that has a spring constant k. So now the mass was initially at x equal to 0, but it is pulled to x equal to a. So now if we draw the free body diagram, that means the force is in this direction, this is w, and this is the n. Now here you can see that the force is in the opposite direction of the displacement. The displacement is in this direction, the force is in this direction. Now after, when we release this mass, the mass will go to x equal to 0, and at this point the F is equal to 0. But due to but the mass has come from x equal to a to x equal to 0, so that means that there is a certain velocity of the mass. So that's why the mass will go to a certain position in this direction, because at this point at x equal to 0 there is a certain velocity. So that's why this is the first scenario, this is the second, now the third. So this is the mass. Here it is x equal to minus a, x equal to 0, x equal to a. So now the mass has come to x equal to minus a, and here the force is in this direction and the displacement is in this direction. Now again it will come to particular, we will have this kind of uh, zero, where f equal to 0, but it will have a motion towards this direction because there is a velocity, and it will repeat, because after this the condition of this mass will be like this. So it will go from 4 to 1, and then 2, then 3, then 4. In this way this periodic motion will happen, and here we can see that f is proportional to minus x. The wave, now this equation is written as f equal to minus kx, where k is the spring constant, now m a equal to minus kx, so a equal to minus k by m x, or x double dot equal to minus k by mx. So this is the equation, or here we can do this simplify like m omega square x. This is the equation of SHM. Now a solution for this particular equation is xt equal to a cos 2 pi by t or a cos omega t. So if we take derivative of this particular equation, we see that x t is equal to minus omega a sine omega t x double dot t equal to minus omega square a cos omega t. So this a cos omega t can be replaced with this, so we can say omega square x. So it satisfies the periodic equation of SHM. So now if we plot this particular equation, then we will see position 0 plus a minus a. Now as this is cos, so it will, I mean, this started with x equal to a, so this will be the plot for the displacement of the mass. So here this is t by 2, this is t, again this is 3 by 2 t. So as you can see here, the position of the mass was a. Okay, this is a certain condition of the mass, and then after t the mass is at the same position. So this is the one oscillation or one I mean, it is completing one cycle of its motion. So that's why you can see it takes exactly t time. Another, in this case, t by 2 to 3t, like minus a to first minus a to second minus a, that is also the difference is t. You can also check that here. But one thing we need to notice about the time period when we are calculating time period, that you cannot say that the time period should be between these 2 points. No, that is not possible, because here the mass is going toward the negative direction and here the mass is going to the positive direction. So these are the different condition of the mass. So you cannot say that here the oscillation is repeating itself. I mean, the motion is repeating itself. So that is not the correct time period. Also, we can represent the displacement of the mass with omega t plus phi. So this will actually change the graph with respect to, like, this is changing the origin. So now it is like here 0 minus plus a minus a. This happened because of the we are having the t equal to 0 at, we are determining the t equal to 0 at different instant of time. For example, here the t equal to 0 at when the mass is at position a, but here the t equal to 0 at when the mass is at 0, x equal to 0. So this phi is known as the phase. Now again xt equal to a cos omega t plus phi x dot t, which is basically velocity, is minus omega a sine omega t plus phi. Now here, if you, as you know, the maximum and minimum value of sine is +1 -1. So omega a minimum of Vt is equal to minus omega. So you can say that Vmax equal to omega a. So Vt equal to minus Vmax sine omega t plus phi. In the same way, At equal to x double dot t equal to minus omega square a cos omega t plus phi. So At max equal to omega square a At min equal to minus omega square a. So At equal to minus a max cos omega t plus phi, where a max equal to omega square. Now here when I put let's say t so there are three condition of x, that is 0, a, minus a. So when x equal to 0, that means that cos of omega t plus phi is 0. So cos of omega t plus cos of omega t plus phi equal to 0, that means that this is omega a and this is also 0. Then at x equal to a, that is cos is maximum, so it will be 0 and it will be minus omega square a, and it is 0, it will be minus. Okay, now another problem we are going to solve, that is, let me write the problem first. A 2 kg block placed on the okay, I'll just write the values of the parameters, that will be better. Okay, so there is a 2 kg block is placed on a frictionless surface, a spring with a force constant, spring with a force constant 32 Newton per meter is attached to the block, and the opposite end of the spring is attached to the wall. So this is the same configuration like this. Now the spring can be compressed or extended. The equilibrium position is marked at x is equal to 0. 0. Work is done on the block by pulling it out to x equal to plus 0.02 meter. The block is released from rest and oscillates between x equal to minus 0.02. The period of motion is given 1.57. Okay, so now we first find the angular frequency. See omega. So before finding omega, we need to know if there is a phase shift or phase in the motion. So as you can see that the x equal to 0.02 and x equal to minus 0.02. So it is basically going like this, plus a to minus a. So there is no phase shift. So we can conclude that phi equal to 0. Now omega equal to 2 pi by t, 1.57 second. So this is 2 pi by 1.57, which is approximately 4 seconds inverse. Now Vmax, which we know is a omega, a is 0.02 multiplied by 4.00, which gives 0.08 meter per second. Now maximum acceleration Mx is a omega square, that is 0.02 into square, it is 4.32 meter per second square. Now we have all these things, omega, a omega square. Now we just need to fill the equation of motion. So x of t equal to a cos omega t plus phi equal to 0.02 cos 4 t. Then Vt equal to minus Vmax sine omega t plus phi, which is minus 0.08 sine 4t, and at equal to minus Amax cos omega t plus phi, which is minus 0.32 cos 4t. So these are the equation of motion for this particular mass. Now as I mentioned, the equation of motion can be given like F equal to minus kx, where from here you can write x double dot equal to minus k by m x. If you compare this with the equation of motion for SHM, you will get omega square is equal to k by m, or omega equal to root over k by m. So now omega is k root over k by m, so t equal to 2 pi by omega, which gives you 2 pi over m by k, and frequency is 1 by t, so k by m. Now this is the problem for the mass that is oscillating horizontally. Now if there is a vertical, now if a mass is hanging from wall with a vertical spring like this, what will happen? When now for example, this is the equilibrium position from the ground, we can say. Why not? Now we pull the mass to the ground, so it will y naught minus delta y. So this is the delta y. So now k delta y, which is k y naught y1. Now there are two forces that is acting on the mass, that is one is Fs and another is the weight of the mass, that is mg. The net force on the mass is 0 at equilibrium. So Fs minus mg equal to 0. So minus k minus delta y equal to mg. Now if block is displaced to a position y, then F net changes to k y naught minus y minus mg equal to 0. K y naught minus y minus k y naught plus ky1. Plus ky plus ky1. Yeah, I don't need these things. So from here we can see that the excess force on the mass is basically F net equal to minus ky, which gives us the T2y T2 equal to minus ky. So this is the same thing for the oscillation happening in the horizontal direction. Now there are some problem we are going to solve about the simple harmonic motion. Which of the following represent SHM? First one is x equal to a sine omega t plus b cos omega t. Again x equal to a sine omega t plus b cos 2 omega t. Third, x equal to a e to the power I omega t. And fourth, x equal to a ln omega t. To obtain the solution here, we need to verify that this equation satisfy the equation of motion for SHM, that is x double dot equal to minus omega square x. So to get this equation, we will start by take derivative of the equation given here. So for the first case, x equal to a sine omega t b cos omega t, x dot equal to omega a cos omega t minus omega b sine omega t, x double dot minus omega square a sine omega t minus omega square b cos omega t. So if we take common of omega square, we are left with minus omega square into a sine omega t plus b cos omega t minus omega square x. So this actually equation of motion of SHM. So first one is actually equation for SHM. Now for the second one, a sine omega t b cos 2 omega t. A sine omega t, b cos 2 omega t is equals to. Now x dot equal to omega a cos omega t minus 2 omega b sine 2 omega t, x double dot minus omega square a sine omega t minus 4 omega square b cos omega t. So here you can see that we, even if we take minus omega square common, we are left with a sine omega t plus 4b cos 2 omega t. So this fourth term actually comes here, and we cannot write omega square x, so it is not a SHM. Again, for the third problem, that is x equal to a e to the power I omega t, x dot equal to I omega a to the power I omega t dot equal to minus omega square a e I to the power omega t, which equal to minus omega square x. Again, for the fourth problem, x equal to a ln omega t. So x dot equal to a by omega t omega, which gives a by t, then x double dot gives minus a by t square, which is not equal to omega minus omega square x, not as it. So in this way, if a equation of motion is given, then we can verify that it is it is a simple, it exhibits a simple harmonic motion or not. Any question? Someone was asking about the link about the previous problem solving session, right? Is he here? Yeah, I have put the link for the previous problem solving session. So the person who was asking about that, you can go to that link. Now there is another problem, which is consider a particle Is there anyone? Consider a particle undergoing simple motion harmonic motion. The velocity v1 and velocity of the particle x2 is v2, so that the ratio of t and a is t by a equal to 2 pi root over x2 square minus x1 square by v1 square x2 square minus v2 square x1 square. T is time period, A is so this is there is the problem that consider a particle undergoing simple harmonic motion. The velocity of the particle at position x1 is v1 and the velocity of the particle at x2 is v2, so that the ratio of time period and amplitude is given by this equation. So now we have to simplify our equation a little bit. A cos omega t, so v is minus omega sin omega t minus a omega root over 1 minus cos square omega t equal to a omega minus x square by a square, which gives omega square minus x square. So basically v equal to omega is root over a square minus x square. So v square equal to omega square a square minus x square. So we are given at x1 v equal to v1 is equal to x1, v equal to v1, and x equal to x2, v equal to v2. So v1 square equal to omega square minus x1 square, v2 square equal to omega square minus x2 square. Now v1 square minus v2 square is, oh sorry, omega square. So v1 square minus v2 square is omega square a square minus x square minus omega square s square minus x2 square. So omega square equal to v1 square minus v2 square by x2 square minus x1 square. Omega equal to root over v1 square minus v2 square by x2 square minus x1 square, and t equal to 2 pi by omega, which gives x2 square minus x1 square by v1 square by v2 square. Also from these two equations, if we divide v1 square by v2 square, omega square a square minus x1 square a square minus x2 square v1 square omega square a square minus v1 square omega square x2 square equal to v2 square omega square a square minus v2 square omega square x1 square. Now a square equal to v1 square omega square x2 square minus v2 square omega square x1 square y v1 square omega square minus v2 square omega square. So v1 square x2 square v2 square x1 square by v1 square minus v2 square. So now we have got the value for amplitude and time period. So basically taking the ratio T by A equal to 2 pi x. So this is a numerical, it's not a numerical, this is basically algebra, pure algebra. So this is the ratio of T by A, T and A, 2 pi root over x square minus x1 square by v1 square x2 square minus v2 square x1 square. Now there is another problem. This is a similar problem that I have mentioned at the start of this particular session. So a nurse measured heartbeat in terms of time period which is 0.8 second. So t equal to 0.8. So what is the heartbeat? So 1 by f equal to 1 by t, which is 1 by 0.8 is 1.25 second inverse. So heartbeat is generally measured in 1 minute. So heartbeat equal to f into 60. So 1.25 into 60, which is 75 beats per minute. Now there is another problem, that is calculate amplitude angular frequency time period. and initial is for the simple harmonic oscillation a y equal to 0.3 sine 40 pi t plus 1.1 b y equal to 2 cos pi t c y equal to 3 sine 2 pi t minus 1.5. Is there any question? So now for simple harmonic motion, we know the equation is y equal to a sine omega t plus phi naught or a cos omega t plus phi naught. Now what we need to do, we need to just compare this equation with the given equation. So now for a, y equal to 0.3 sine 40 pi t plus 1.1. So here a equal to 0.3, this is the amplitude. Angular frequency is omega, so omega is 40 pi rad per second inverse. So frequency is f omega by 2 pi, so that will be 20 hertz. Time period t equal to 1 by f, that is the 0.05 second, and initial phase is 1.1 rad, this one. Now again for b is very simple, y equal to 2 cos pi t. So here a equal to 2 omega is equal to pi radian per second. So f equal to omega by 2 pi 0.5 hertz. T time period is 1 by f, so it will be 2 second. Initial is 0 radian because there is no term with the pi t. Now for c, y equal to 3 sine 3 sine 2 pi t minus 1.5, 2 pi t minus 1.5. So a equal to 3, omega equal to 2 pi, f equal to 1 hertz, t equal to 1 by f, so that is also 1 second, and then the phi naught equal to minus 1.5 radian. Then this is the last problem. After that I will move to the Mathematica to show you some codes. So that for a simple harmonic motion, the phase difference between a displacement and velocity is pi by 2, b v and a is pi by 2, c x and a is pi. So basically here we need to verify that the phase difference between displacement or x and velocity or v is pi by 2, the phase difference between velocity and acceleration is pi by 2, and phase difference between displacement and acceleration is pi radian. For that we will start with y equal to a sine omega t. Now v is a omega cos omega t, which is a omega sine omega t plus pi by 2, and for a minus omega square a sine omega t, which is omega square a sine omega t plus pi omega t plus pi. So clearly here you can see that the phase difference between displacement and velocity, or displacement and velocity, is pi by 2. The phase difference between velocity and acceleration is also pi by 2, and if we see the phase difference between the x and a is pi. So these are the numericals. Now I will go to the Mathematica. Is my screen visible?
Now it's visible.
Yeah, thank you. So yeah, so this is a basically animation of the simple harmonic motion which is made by the Wolfram demonstration project. It is available in the website of the Wolfram. If you search simple harmonic motion in demonstration in Wolfram Mathematica, you will get this. So from there I have downloaded it. So now here you can see two kinds of simple harmonic motion, spring and piston, where this particular bead is actually showing the position of A at this circular motion. So now if I move the amplitude, you can see that there is the compressing and stretching of the spring is happening, and so that if we map the position of the bead to a circle on the circumference, so there we can see a motion. So this motion is actually simple harmonic motion, where this OA is the radius r, OB is the x, and this is y. So OB is x and BA, this height is y. So OA is basically root over x square plus y square. So now this theta is equal to omega t. Now x can be represented as r cos omega t and y is r sin omega t. So when we check this motion, we can see that this the y part verifies the simple harmonic motion, y double dot equal to minus omega square y. This can be also shown for the piston. So this is a demonstration available in the website of Wolfram, and also you can see the source code of this if you search, but that source code is very lengthy, so I have not displayed here. Now the example I have shown in numerically, now I can show that in the in Mathematica software. So basically here we will use the dsolve command and write the plus square star y of x x. So here you can see that the equation for this simple harmonic motion is yx equal to c1 cos x omega plus c2 sin x omega. Now I will plot the problems I have shown in the sample. 40 star pi star t plus 1.1 2 cos pi star t 3 star sine 2 pi t pi minus 10 to 10 range is very big for this 3 motion. So here you can see that for 0.3 sine 40 pi omega t plus 1.1 we got the amplitude is 0.3. So here you can see that the oscillation is not big, but the frequency is very big because the frequency we got was 20 hertz, and there is a phase of 1.1. So if we zoom it to here, we can see that this oscillation is not exactly maximum at the 0 or not minimum at the 0 or not 0 at 0. So we can say there is certain phase. Now the second motion, that is 2 cos pi t, where there is no phase, so it is perfectly maximum at t equal to 0, that is x equal to 2. So where the frequency is 0.5 hertz, and the initial phase is 0, the time period is 2. So basically time period is 2 means that it is reaching the displacement 2 at 0 and then again at t equal to 2. Now the third one is the 3 sine 2 pi t minus 1.5, which is the amplitude is 3. What you can see from this particular plot, that the green line is going from -3 to +3, and then there is a uh, time period of 1 second, so it is going to -3 to again -3 and t equal to 1, and there is the initial phase of 1.5. So all these things can be seen from this particular plot. Now again in LC circuit we see that the same kind of differential equation, which is q t plus q t Hmm. So now this is the differential equation we get from a LC circuit, where the Q denotes the charge and L and C are the constants. So and Q equal to at Q equal T equal to 0, the charge is maximum, that is A, and at Q dash 0, that is the current, that is Z, 0 at T equal to 0. These are the two boundary conditions. So when we solve this equation, we get Qt equal to A cos T by root over LC. This is the solution for this uh, differential equation. Again, what I have shown by when I discussed the problem, which of the following equation represent SHM, I used 4 equation and then took two second derivatives, took two derivatives to verify that the expression verifies satisfy the x double dot equal to omega square x or not. So for that, what I have to write is omega t into a sine omega t plus b cos omega t. So this is the way you write a function in Mathematica, yt underscore y under this bracket t underscore colon equal to a sine omega t b cos omega t. So this is a function of t I have written. Now what I'll do, I'll just take the first derivative first, y t. So here the first argument is yt, that is the function, and then the variable with respect to I am going to take the derivative. This is the first derivative, that is a omega cos t omega minus b omega sin t omega. Okay. Now again I will do the second derivative, this d y t comma t. So this is the second derivative of the equation yt. So minus b omega square cos t omega minus a omega square sin t omega. Now if we simplify that, we get minus omega square b cos t omega a sin t omega, which is exactly the yt. So we can say that the double derivative is equal to minus omega square. So in this way we can understand that this particular equation actually satisfy the simple harmonic motion. Now okay, so here this some kind of problem with this particular plot. Okay, this plot is not working here. Yeah. अरे So this is a plot for the sine omega t plus phi. Now what I am going to show you, that is a sine omega a t plus phi. Here you can see that these are the two graphs where this is the first one is the x, and then second one is the x dot t, that is the velocity. So these two have a phase difference of pi by 2. Again, this three graph shows that there is the between the displacement and the velocity, the phase difference is pi by 2. That is phase difference between the velocity and the acceleration, the phase difference is also pi by 2, but the phase difference between the displacement and acceleration is actually pi. Now here I am going to write a code to find the root of a equation. So manipulate lot log of x comma x to the power 1 by 3 x 0 b. Lot legends expressions b 1 to 150 step of point 1. So here so these are the two graphs. So now as I change the value of b, I can see that the these two graphs are intersecting at two different points. One is here and another is here. So first one is around 5 or 6, and the second one is around almost 90. Okay. So as we have verified that there is two points where these two graphs are intersecting. So we can now try to solve it in numerical solve. So when we solve equation using solve equation numerically, we use n solve. So log x so x to the power 1 by 3 equal to 0. So first I have written the equation, then the variable. Now this is the equation, but NSOL is giving some kind of warning, so I will use another function, that is reduce. So first one is x equal to 6.40567, and the second root is x equal to 93.3545. Now we can change this. Uh, which minus sign you are talking about, Arif?
Hello, am I audible, sir?
Yes, yes.
Sir, that minus sign between two functions, that is log x minus x raised to 1 by 3.
Okay, so this is basically, I mean, so when we are trying to find the value of the intersection, okay, this is for 2. Yeah. So we are trying to find the intersection, right? So at particular these 2 points, the value of these two log x and x to the power 1 by 3 are equal. Okay, so when we take the minus sign, that should be equal to 0. So basically nsolve is give us the solution for the equation. So nsolve log x minus x to the power 1 by 3 equal to 0 will give the solution for the intersection. Like if I write nsolve, for example, we have a equation 2x equal to 3, right? So now if I 2x equal to 3 0 x equal to 1.5. So 2x has a different line and 3 has a different line. Now if I do the same thing, ah,
Okay, sir, understood.
okay, got it.
Instead of the minus sign, can we also go directly like log of x equal to x raised to 1 by 3?
That I think you can also do. Let me check. I'm not sure about it.
And we can remove that equal to 0.
Yeah, the same thing is happening. 6.50567 and 93.35. So you can go both way.
Okay, sir, thank you.
Okay, now if I replace this with 2, then here you can see that this there is no intersection. So basically it is not actually intersecting with the log x graph. Sorry. Now here you can see the log x and x to the power 2 by 3 minus 1 has 2 intersection point. So we can use that. Looks like it's taking longer than expected. Yeah, so these are the two solution for this particular equation, that is x equal to 1 and x equal to 3.139. This is how you solve it and find the root. Now again there is a problem using manipulate. So manipulate plot x plus b plus b square plus c 1 x So ax square bx plus c is a quadratic equation, general quadratic equation, and minus b square by 4a plus c is the minimum value of the equation, as you can turn this ax square plus bx plus c into a perfect square, and the perfect square, and then you will have a extra term that will be this one. So the perfect square term will go up to the minimum value of that perfect square part will be 0, and this is the term that will you are left with. So now if I change the value of b, you can see that at every value of b, this parabola is touching that straight line, that is by the minus b square by 4a plus c. Now I will show something from the mathematical desktop, because in this will form the lot of problem. Yes, so this is a problem of electric field lines of a quadrupole. Plot the electric field lines and equipotential surface of the quadrupolar configuration. Force charges of same magnitude and alternating sign on the corners of square side A, that is plus q at 0 0 and A, while minus q at A 0 and 0. So now this is I have shown it for the dipole in the last class. Now it is for the quadrupole. So when I run this equation for the quadrupole, I get the field lines like this, where these four are the circle denotes the position of the charges, and then this is the plot for the field lines. Then there is the equipotential that is denoted by this one, 1 by r minus 1 by r1 minus 1 by r2 plus 1 by r3, where the position is defined as root over x square plus y square, x minus 1 whole square plus y square, x square plus y minus 1 whole square, and x minus 1 whole square plus y minus 1 whole square. So this show the equipotential and field lines together. So this is the exact plot for the quadrupole, as I have shown in the previous class about the dipole. Now this is for a magnetic dipole, that is 1 by r cube. Basically this is the magnetic dipole loss, where 1 by r cube multiplied by 2 x square by r square minus y square by r square. These are the x and y position. Now if I plot that, we will get this kind of magnetic field lines. Also this is a series expansion for the cos hyperbolic, which gives us the 1 plus x square by 2. Now if we plot together the cos hyperbolic x and 1 plus x square by 2, we will get this kind of plot, where you can see from this there we have exactly almost same value for these two plots. So here we have compared the value of cos hx and the series of cos hx and absolute value of cos hx with respect to cos hx for x equal to 0.5, and we can see the difference is 0.00232876. So now if we change the value to 1, that is also decreasing to 10 to the minus 6, and if the value is around x equal to 1, then the value is like 0.0279, where if we increase the value, we'll get 0.2, and if we increase the value further, we'll get 0.760429. Now you can see that now if we do the same thing with the sine hyperbolic, we get that the series expansion of sine hyperbolic for the range 0 to 2 is x. Now if we plot, we can see that in this region it is exactly matching with the sine hyperbolic x and x. Now again if we do the same thing, sine hx, at point 1 you can see that this is giving 0.0000016592. Now if we change the value, you can see that the value is increasing. So in this way we can actually say for which range we can approximate the sine hx with x. For sine curve also this can be possible with as we have seen a lot of times that we are approximating the sine x with x. So in this particular region it is matching with the sine x term. Now we will see for tan x. For tan x also the series can be up to x, but when we increase the range can be up to increase the order. We can see that x plus x cube plus 2x to the power 5 by 3 by 15. Now you can see that this yellow line is the simple x, and then this is the green line is showing the x plus x cube by 3 plus 2x to the power 5 by 50. So these are the approximation, depends on what accuracy we need for calculation. So according to that we choose our approximation, but mostly for tan x and sin x we need only up to the first order approximation, and we can use that. And in this way we can particularly find the difference between the absolute value and the approximated value. So this is the last thing I have to show today. Any question?
No question from my side, sir.
Okay.
So
So
that, yeah, YouTube link you shared, that is for the first session, and this is the third one, right? So I missed second session, sir, and I'm interested to watch it again.
okay, the
Second
second
session.
session. Actually, the second session you are talking about, that is conducted on Saturday, right?
Yes, sir.
That is conducted by a different person, so I cannot have. I don't have that link. So you have to contact the NPTEL or whatever you can contact, but that link I don't have.
Okay, sir.
Okay.
So these tutorials are lagging behind the assignments. So it's a bit difficult to solve that problem.
Yeah, that I know, but we are instructed to start our class from the last week. So, I mean, I cannot jump to the current assignment, because then in the last class I'll be left with, I mean, no problems. You can understand that. So I have to do that. But I
Okay.
will try to include some current problems. I'll try to do that in the next session, definitely.
Okay, sir. Thank you.
Okay. Okay, so now if there are no doubts, then I will end this today's class.